Hello and welcome, ladies and gentlemen. We are looking at activity 3.2 of this packet 3. I realized in my last video, I told you in the last video how I used my brother's printer and some stuff was missing. Well, I realized that the titles of these was also missing, so I just wrote this in. Constructing an inscribed hexagon. So as you can guess, for activity 3.2, we are going to be doing just that. We're going to be constructing an inscribed hexagon. So here we have this little paragraph here. It says, in the getting started, you created an equilateral triangle by duplicating the length of the radius to create a chord. You can use what you know about copying a line segment to construct a regular hexagon inscribed in a circle using a compass and straight edge. So here we have a little definition over here. An inscribed polygon is a polygon drawn inside another polygon or circle in which all of the vertices of the interior polygon lie on the outer polygon. So like in the last packet when we were doing those mid segments and we were creating quadrilaterals inside of quadrilaterals, those are inscribed polygons. So if you don't know what a polygon is, it's a shape with straight, this isn't the exact definition, so excuse me, it's been a while since I've defined a polygon. It's a shape that is enclosed, meaning that like if you were to put sheep in it, they couldn't just walk out, right? So it's enclosed, and the sides are all straight lines, and I believe that's I believe that's it. But anyway, so a polygon, and then inscribed, like we talked about, scribed means written, and then the prefix in there means inside. So it is a polygon that is written inside of something, inside of another polygon, in fact, or a circle. So there you go, there's that definition. Okay, so now looking over here, we have one says use circle A to complete your constructions. This is circle A over here. It says copy the radius of circle A. So the best way that I think to do that, so there's a couple ways that you can do this. You can draw the radius with a straight edge, and then you can measure it. That's one way that you can quote unquote copy it. The way that I would copy it is just using my compass. I would put the point of my compass on the center on point A here, and then I would make the width or the arc of my compass equal to the radius, so that when I put down the arc of my compass, it rests on the circle. So now my compass is ready to go. It is sitting there, and its arc is equal to the radius of the circle. Okay, and then so now I'm looking at, so copy the radius. So I've done that. I haven't really done much with it yet, but I have done that. So here we go. So now part B says create 6 chords around the circumference of the circle A so that they are congruent to the radius and their endpoints are equidistant from each other. So basically what this is saying is just to create 6 chords with this length here. So a chord has both endpoints that are on a circle. So I'm going to move this to the center here so that you guys can see it. A chord has both endpoints that are on a circle. So what I'm going to do is just start by drawing a point on my circle, literally anywhere. Okay. So, and then from that point, I'm going to go ahead and use my arc that I have here, my radius, and I'm going to put the point on the, I'm going to put the point of my compass on the point that I just constructed on the circle there. And then I'm just going to make a little arc mark. Sorry, I was way off the screen there. Okay. And then, sorry, I got a little distracted there. Got a text message. I'm just going to flip my phone over. Okay, don't be a distracted YouTuber. Here we go. So then I'm going to put the point on this intersection that I just constructed here, and then make another arc. And I'm going to do this 6 total times. Okay, and after I do it the 6th time, so I know my markings are kind of light and the shadow's kind of tough, but hopefully you can see my arcs that I'm creating here. Okay, after I do this, hopefully if I do it right on the 6th time, so on this time, I would make it so that the arc I construct goes exactly through my original point, which it did, so that's good. So now all these marks, what do I do with those now? Well, now I need a straight edge, which mine is right here. Here we go. So now I need a straight edge, and to create these chords, I just need to connect, so all these points, these intersections here, I'm just gonna connect all of these with a straight edge. So, and I'm not going to do anything crazy. I'm not going to go across the circle. I'm just going to connect the ones that are closest to each other, or yeah, the ones that are closest to each other. If you wanted to say that they're adjacent, technically, I don't think that you'd be wrong. They are the ones that are closest to each other. Okay, so here we go. There's 2 sides from there, and I apologize again about the shadows and just like maybe not being able to see this all as well as you would like. This is just kind of how I have to do constructions on these videos with how I have my setup here. So I could have done the construction before, but the whole point of this section is learning how to do the construction, so I wanted to show you how to do it. So there you go. So now I've created 6 chords. I've done part B. That's good. Oh, connect consecutive endpoints of the chords. Okay, that's there we go. That's what we did there. So there's that. And then, so now it says the figure you constructed is a regular hexagon inscribed in a circle. So y'all know what a hexagon is. It's a polygon with 6 sides, which if we count 1, 2, 3, 4, 5, 6, that all fits. And then regular, what that means is it's just got all side lengths. It's got all of its side lengths are congruent, and all of the inscribed, or all of the interior angle measures are also congruent there. So a regular polygon is a polygon with all sides that are the same length and all interior angle measures that are the same as well. So now 2 says, how can you copy an angle to verify that the inscribed hexagon is a regular hexagon? So this is just asking how you can do this. Oh, and then actually they do have a little definition of a regular polygon. A regular polygon is a polygon with all sides congruent and all angles congruent. So there you go. Basically what I said. Didn't realize that was there. So now number 2, again, how can you copy an angle to verify that the inscribed hexagon is a regular hexagon? So basically it's asking, how can you copy an angle to tell that all of these angle measures are the same measure? So you can just talk about how you could duplicate an angle. So and I'm not going to write all this because it's just going to get kind of wordy. So I'm just going to, I guess I will write this. Duplicate an angle. Okay, and then my explanation here is what's important. So if I were to duplicate, so let's say I look at this angle right here, this bottom one right there. If I were to look at that angle and I wanted to duplicate it, well, if I duplicated this angle onto this line right here, if I duplicated it and the angle that I created didn't fall exactly on this line as well, right? So I'm going to cheat a little bit. I know that this this angle measure is 120 degrees. So if I duplicate this 120 degree angle onto this line, this chord right here, this like bottom left one, okay, or like this far left one, if I were to construct a duplicate of this angle onto this line, the other line that I construct should fall exactly where this one is. If it doesn't, that means that these 2 angle measures, the one that I have already right here and the one that I have here, are not the same, because with the one I constructed should line up. So here's another way to say this that maybe is a little less confusing. So if I have a 90 degree angle, right, and then I wanted to check to see if it's the same as this other 90 degree angle, what I would do is I would duplicate this angle, this first one, angle 1 here, onto angle 2, and if it didn't match up perfectly, like if it didn't match up exactly at 90 degrees, then this one would not also be 90, right? So I guess a third way to look at it, if this is helpful for you as well, say I have a 90 degree angle and then I have one that's not 90 degrees, and it says duplicate angle 1 onto angle 2 so that you can verify that they're the same angle measure. Well, when I copy angle 1, okay, so here's angle 2, this like 45 degree looking one, right? If I were to copy angle 1 onto 2, it would look like a 90 degree angle, right? And that's obviously, these 2 angles are obviously not the same, which means that these 2 angles are not the same measure. So angle 2 was this 45 degree one and angle 1 was this 90 degree, which we can tell just from looking, but if you wanted to prove it by this duplication, you could duplicate angle 1 onto angle 2 and see that because they didn't match up perfectly, they weren't the same. Whereas if you had a 90 degree and a 90 degree and you duplicated it, it would match up perfectly. So now going back to this, if I have 120 degree and it's a regular polygon, all of these should be 120 degrees. But if I copy this, if I duplicate it onto here and it doesn't match up perfect, then I know that I have done something incorrect there, okay? So that's how you can verify it, that it is a regular hexagon. Cool. So now, question 3. What do you know about the measure of the interior angles of a regular hexagon? So I kind of cheated a little bit. And I didn't realize that this was the next question when I said that, but they are all 120 degrees. Now, the way that I know that, okay, so if you remember from the last exercise, we constructed this hexagon by making triangles. So I'm going to freehand this, okay, so forgive me if this isn't perfect. So we constructed this hexagon in the last exercise, in the last activity, by making these equilateral triangles. And so one thing that we said about the equilateral triangles is that they all have interior angles of 60 degrees. So this angle measure, so say if I were to label this, angle measure ABC is equal to this 60 plus this 60, which is 120. And because I had these triangles all the way around the hexagon, if I were to add up all of these, I would get 120 for every single interior angle of the hexagon, right? So all the triangle measures are 60, but when I add those up for the interior angle measures of the hexagon, I get 120 for each one, right? Because 60 plus 60 is always going to be 120, and I just am doing a bunch of 60 plus 60s there. So there you go, 3.2, pretty short activity, not too bad. I hope you guys all have a wonderful evening. If you have questions on this, ask me in class. Let me know what you think. I hope you guys have a wonderful evening. You're wonderful people, and I will see you all in class. Adios.